Hello everyone. In the previous session, we have discussed about, I have explained you about the constructional details of the synchronous generator and the working principle of the synchronous generator. So that is the first part in this chapter, that is in synchronous generator. And remember, the synchronous generator can also be called as AC generator, and so it can also be called as alternators. And we have also discussed along with the working principle and constructional details, so we have also discussed about the different types of rotors in the synchronous generator. So there are two different types of rotors. So one is a non-salient type of rotor and another one is salient type of rotor. Okay, I hope you are familiar with these topics. In the next part, so we are going to derive the expressions of the frequency and the induced EMF. So in the first part, let's see the equation for the frequency of the induced EMF. Okay, and once we derive the expression of the frequency of the induced EMF, so later we can derive the induced EMF equation or the average EMF. And here the design of the alternator is made. The design of the alternator is made such that the here the distribution of the flux, right? The distribution of the flux is flux around the air gap circumstances is sinusoidal wave. Okay, so I'll just repeat, the design of the alternator is made such that flux distribution or the distribution of the flux around the air gap circumstances is sine wave. So therefore the resulting voltage or the resulting EMF, so here in any one armature coil, the resulting EMF in any one armature coil varies sinusoidal with time. Okay, remember it varies sinusoidal with time. And so we know that the one rotation of the rotor or one revolution of the rotor represents 360 degree. So remember, so one revolution of the rotor represents 360 degree. So one cycle of EMF is produced. So remember, one cycle of EMF is produced when a pair of poles, when pair of magnetic poles passes a conductor. So what is the meaning of this? So you can just see here, and so this part is, so these are the conductors which are placed at the stator, and these are the poles, you can find it in the rotor. Okay, so this completes, this is the rotor part and this is the stator part. Okay, so here I have indicated that one cycle of EMF is produced. When it produces one cycle of EMF, that is when a pair of poles passes a conductor, when a pair of poles, right. So here, so you can see north and south pole, when a pair of poles passes this conductor, like each conductor, so it will produce one cycle of EMF. So, and if the machine has P number of poles, what happens when machine has P number of poles? So here I'm talking about one cycle is produced when a pair of poles passes a conductor. Okay, and if a machine has P number of poles, then how many cycles of EMF it produces, how many cycles it produces? So that we are going to see. If machine has P number of poles, remember a number of cycles in EMF is equal to P divided by 2, right. If machine has P number of poles, then number of cycles, okay, so in EMF, that especially for one rotation, for one revolution, so we get P by 2. So let us consider if P is equal to 2, assuming we have two poles. So if P is equal to 2, then what happens? The number of cycles in EMF in one revolution becomes, so it is 1 if P is equal to 2. This is just an example, but the general equation says, so number of cycles in one revolution is equal to P divided by 2. And so similarly, number of revolution per second. So here we are going to have another equation, that is number of revolution per second. So we are talking about per second, then so we get N divided by 60. So N indicates the number of revolution, or we also consider the speed. So we also consider n as speed in terms of RPM and it is per second, then we get n divided by 60. So let us call this equation as 1 and let us call the another equation as 2. Okay, then, so based on these two equations, so we are going to derive the frequency equation. How do we define frequency? So we know that frequency is equal to, so it is number of cycles per second, right? So you know this, isn't it? So number of, like frequency can be defined as number of cycles per second. So here from this equation, frequency equation, so we are going to divide or we are going to split into two, which is frequency is equal to, so number of cycles per revolution into, so revolution divided by seconds. Look at this. So here when revolution gets cancelled, finally you get number of cycles per second, which is same as the frequency. So here we have taken in two different forms. So number of cycles per revolution. Now what is number of cycles per revolution? As we have already defined in equation 1, that is P divided by 2. So number of cycles per revolution is P by 2 into what is number of revolutions per second? Number of revolutions per second is n divided by 60. So n divided by 60. So here what is frequency then? So frequency is equal to np divided by 120. So here f is the frequency and where n is the speed of the rotor in RPM, revolution per minute. So RPM, then p is nothing but the number of magnetic poles. F is equal to, finally we have obtained f is equal to np divided by 120 and let us call this equation as 3. Now based on the equation 3, that is frequency equation, we are going to derive EMF equation. Now we shall derive the EMF equation of a synchronous generator. So here to derive the EMF equation of the synchronous generator, here we need to derive the equation for and considering this one revolution of rotor. So remember, that is by considering one revolution of rotor, so we are going to derive the EMF equation. And remember in the first case, so we need to have the magnetic flux cut by one conductor. So you know this, right? The magnetic flux cut by one conductor or the conductor cut by the magnetic flux, whatever. So there will be a change in flux. Right? Or when you can see the change in flux, that is magnetic flux cut by one conductor or conductor cuts the magnetic flux. And the change in flux, so this can be considered as the change in flux. So change in flux, so can be represented as d phi and d phi which is equal to p phi. So p phi, since the change in flux depends on the number of poles which are made or which are constructed in the rotor, it is d phi can be considered as p phi. Call this equation as 4. Because we have taken equation 3 in frequency equation, and here the time taken to complete one revolution. First case, so we have seen d phi is equal to p phi, and in the second case time taken to complete one revolution. Then so how much time it needs to complete one full revolution, that can be considered as dt, that is change in time. Right? So and change in time or the time taken to complete one revolution is 60 divided by n, because we are considering for one revolution, it is time taken per this revolution or one revolution, and this we consider as 60 divided by n. Let us call this equation as 5. So after considering equation 4 and 5, we need to have the average induced EMF per conductor, And what is average EMF induced per conductor? So we know that average induced EMF can be defined as d phi by dt, isn't it? The change in magnetic flux with respect to the change in time. So what is d phi? So let us substitute the equation 4 and 5 in this equation. D phi is equal to p phi and dt is equal to 60 divided by n. And further this equation can be written as n p phi divided by 60. right? And as we have derived the equation of frequency, which is F is equal to Np by 120 in the previous equation, that is in equation 3. So here, and what is Np? To have only Np equation, we can have this equation as 120 into F. So what is Np? Np is equal to 120 into F. Let us substitute Np here to get the average induced EMF. So what is Np? Np is equal to 120 F phi divided by 60. Finally, this can be written as 2F phi. This is the average induced EMF per conductor. Once we find this equation, we need to have the same equation for by considering Zph conductors, that is number of conductors. In the next step, we are going to have the same equation, that is average induced EMF, by considering Zph conductor. For Zph conductor, this equation becomes, earlier it was only 2Fi, and this equation becomes 2Fi Zph. And remember, we are going to have another terms, that is T, where T is equal to number of turns, and Zph is equal to 2 into T, where Zph is the number of conductors and T is the number of turns. So here we are going to replace Zph as 2T, and finally we are going to get E average as, finally we are going to have E average as, substitute this Zph here, which is 2T, and this becomes 4F phi T. Okay. So here we have derived only average induced EMF, and further we need to have this equation in terms of RMS value. As I have already discussed how we can convert the average induced EMF into RMS value, that is using the form factor equation. Next we are going to express this average induced EMF into RMS value, the average or the RMS value of the induced EMF per phase. So per phase we express it as, and we know that RMS value is equal to average value into form factor. I hope you remember the concept of form factor, and substitute here. What is the average value? Average value is 4F phi into T into, and what is form factor? So there is a standard value for form factor, which is 1.11, and this is RMS value, and we express it as capital E. So what is finally E? E is equal to 4.44 F phi T. So now this is the equation of RMS value of the induced EMF per phase. Here after deriving this expression, we need to consider the winding factor. So remember here due to the winding factor, so that is the coils are short pitched, we represent it as K suffix C, and the distributed type and we represent it as K suffix D. Okay. So based on the winding factor, now the coils are short pitched and the distributed type, which are considered as Kc and Kd. Finally the E, that is the RMS value which is reduced by this Kc and Kd. Finally the equation can be expressed as EPH. Why it is pH? This is per phase. So here we have derived the RMS value of the induced EMF per phase. EPH is equal to 4.44 F phi T, that is into Kc into Kd, because the total EMF, that is total E, which will be reduced by this Kc and Kd. Finally, if we want to express that E line, that is EL, already you are familiar with the concept, that is relationship between the line values and the phase values, line voltage and the phase voltage. Similarly, we are going to express the same induced EMF in terms of line. EL is equal to which is root 3 into EPH, as we have already discussed in the 3-phase circuit. So we have derived the expression like VL is equal to root 3 VPH. Similarly, we are going to express the induced EMF EL is equal to root 3 into EPH. And remember, this Kc and Kd becomes Kc is equal to 1 and Kd is equal to 1. That is in the case of when the coils are full pitched instead of considering short pitched. So remember, the parameters Kc and Kd depends on how the coils are, constructed in the rotor. So the coils are short pitched and distributed type. So we will have this Kc and Kd value in terms of the fraction that varies from 0 to 1. And similarly, when Kc is equal to 1, Kd is equal to 1. So when do we get this value? That is when the coils are full pitched instead of short pitched. If we find full pitched, then we can consider Kc is equal to 1. And similarly, instead of having distributed type, if we consider concentrated type, then we can have Kd is equal to 1. Only when the coils are like full pitched and the concentrated type, then we can have Kc is equal to 1 and Kd is equal to 1. Okay. So under this winding factor, there are two types. One is pitch factor and another one is distribution factor. So what is this pitch factor? And as I have already indicated, pitch factor is represented as, or it can be denoted as K suffix C, and which is the ratio of the resulting EMF, that is when coil is short pitched, okay, to the EMF when coil is full pitched. So what is the difference between this short pitched and full pitched? And here if the rotor takes one full cycle, and we know that it represents 360 degree, okay, for one revolution it takes 360 degree, and that we consider it as full pitched, okay. So when it completes one full rotation, then we consider it as full pitched. And similarly, if there is any delay, okay, when it stops with some delay, that is some angle like alpha, then we call it as short pitched. So instead of completing one full revolution or one full rotation, if it stops somewhere else with some delay, then we consider it as short pitched. So here remember, the pitch factor is the ratio of the EMF when the coil is short pitched to the EMF when coil is full pitched. Similarly, we have another winding factor, that is distribution factor, and here we denote this as Kd, okay, K suffix D, and this is nothing but the ratio. It is defined as the ratio of the resulting EMF when the coils are distributed to the EMF when coils are concentrated, and the distributed and concentrated. Here how the coils are wound, if it is wound closely, then we call it as concentrated, or if it is distributed, then we consider how here the coils are distributed. If we consider the ratio, if we take the ratio of the resulting EMF, if we take the ratio of this, that is distributed and the concentrated, that is nothing but distribution factor based on this Kc and Kd. Based on the Kc and Kd, finally we derive the expression of induced EMF. So remember, when this Kc and Kd becomes 1, that is the pitch factor when it is full pitch, Kc becomes 1. Similarly, when the distribution factor, when it becomes concentrated, Kd is equal to 1. So this is all about the concept of winding factor. Now we shall move on to the problems in the synchronous generator. Look at this problem. It's 6 pole, okay, so P value is given, a 6 pole 3 phase 50 hertz. Okay, I will write one by one data which is provided in the problem. Frequency is given as F is equal to 50 hertz. So this is the given data, and P is equal to 6. Then alternator has 12 slots per pole. Alternator has 12 slots per pole and 4 conductors per slot. Remember, so you can just read through once again the first line. There are 6 poles here and the frequency is given. Then the alternator has 12 slots per pole and 4 conductors per slot, right. So later I will slot a flux of 25 milliweber. So flux means phi value is given, which is 25 milliweber. Is sinusoidally distributed along the air gap. Determine the line EMF. What we need to find out? The line EMF means we need to find out the value of E line. Okay, line EMF if the alternator is star connected. So here the alternator is star connected because they have provided it is a 3-phase circuit. So of course the alternator, or if we consider the induction motor, all are 3-phase circuits. So here we don't much concentrate on so what type of circuit it is. It is just given as alternator is star connected, and of course the Kd and Kc values are provided here. Okay, so Kc and the pitch factor and the distribution factor values are given here. So Kc and Kd, Kc is equal to 1 and Kd is equal to 0.96. Finally, our objective or our aim is to find out the value of E line, which is the line EMF. And you know that line EMF is nothing but root 3 into EPH. Fine. As we have already derived in the previous part, E line is equal to root 3 into EPH. And to find the value of EPH, right. So what is EPH equation? EPH is equal to 4.44, then F phi T, right, Kc into Kd. Now look at the equation. So we have 4.44 F phi T Kc into Kd. What is F? F is nothing but the frequency. So frequency value is given in the problem. And what is phi? Phi is the magnetic flux, which is also provided in the problem. Of course the Kc and Kd values are given. So now we need to find out the value of T. So what is T? T is nothing but the number of turns. And you know the relationship between the T and ZPH. So ZPH is equal to 2 into T. How do we find the value of T? T is equal to ZPH divided by 2. But so we need to find out the value of ZPH. So what is ZPH? So remember here the main the main part is to find the value of ZPH. So ZPH is equal to, okay, so which is number of poles. So this is very important task here. ZPH is equal to number of poles into number of slots per pole into number of conductors per slot divided by 3. Since we are finding it for 3-phase, since we are finding the number of conductors in 3-phase, we are dividing this by 3. And what is the equation? I will just repeat. ZPH is equal to, what is Z? Z is nothing but the number of conductors per phase. Number of conductors per phase. So ZPH is equal to, which is equal to number of poles into number of slots per pole into number of conductors per slot. You can just look into this equation. So when here number of poles and number of poles gets cancelled, and number of slots and slots gets cancelled. Finally, what do you get here? What is ZPH? As I have already told you, ZPH is equal to number of conductors. Don't you think when the number of poles and number of slots and slots gets cancelled, you get finally only number of conductors? Yes. So ZPH is equal to number of conductors per phase. So since we are calculating this for the 3 phase, we are dividing this by 3. This is very important. Calculating ZPH is very important here. And now we need to substitute all the values. So what is number of poles? Number of poles are provided here, which is 6. Right? So 6 into, and what is number of slots per pole? Number of slots per pole is equal to 12. Then what is number of conductors per slot? So it is 4. It is clearly given in the problem, 4 conductors per slot. So 4 divided by 3. And if you further simplify this value, which is ZPH, then you will be getting 96. Right, as I have already written here. So ZPH is equal to 96. And once you get the value of ZPH, you need to find out the value of T. So what is T? T is equal to ZPH divided by 2. So 96 divided by 2, which is 48. 48, and substitute the value over here to find the value of EPH, where EPH is equal to 4.44 into 50. Frequency is 50 into 5 is, so 25 milli. 25, since it is milli, we need to have into 10 power minus 3 into what is T? T is equal to 48, and what is Kc? Kc is equal to 1, and so what is Kd? Kd is 0.96. So simplify this equation, then you will get EPH as 255.744 volts in terms of volts. But finally what we need to find? We need to find the value of E line. So what is E line? EL is equal to root 3 into EPH. So substitute this EPH here, then you will be getting E line as 443 volts. So this is how we can calculate the value of line EMF. Or now we shall move on to the next problem, and in this problem you can see P value is given, number of poles are given, and alternator has an armature with 90 slots and 12 conductors per slot, of course, which is similar to the previous problem, but here, so you have to observe the problem very carefully. Here the values which are provided here, value which is provided here as 90 slots. So compare this problem with the previous problem. In the earlier problem it was given as, what was the unit? It was slots per pole. So remember, in the previous problem it was slots per pole, but here the value which is given here is 90 slots. It is not per pole. So you have to be very careful while simplifying the value of ZPH. 90 slots and 12 conductors per slot, and it revolves in some RPM, which is n is equal to, it is a speed of the rotor in RPM. So remember, if the value is provided in terms of RPM, which is nothing but the value of n, okay, it revolves with the speed of 1000. RPM means it is the value of n, and 5 values, magnetic flux is given here, then the winding factor is 0.97, and it is clearly given the coil is full pitched, and you know that when the coil is full pitched, then we consider, so they have not given directly Kc, and Kc is equal to so and so and Kd is equal to so and so. Here in the problem itself, the coil is full pitched. You know that when the coil is full pitched, we can consider Kc is equal to 1. And another value, the winding factor. The winding factor is 0.97, then it is understood that Kd is equal to 0.97. So instead of this, if the distribution factor is concentrated, directly you can consider Kd is equal to 1. But here the Kc is equal to 1 and Kd is equal to 0.97. So finally we need to find the value of EL, which is the line EMF. And so you know that to find the value of EL, so which is equal to root 3 into EPH. Fine. And what is EPH? You know that EPH is equal to 4.44 F5 T Kc into Kd. Okay, fine. Here to have all these values. Here look at the problem, frequency is given, frequency is not given here. How do we find the frequency? So remember, in some problems the frequency value will be given, but in this problem the frequency value is not given. When frequency is not given, so you can find out the frequency which is equal to, and which we have already derived, f is equal to np by 120. In the same session we have derived the frequency expression, which is np divided by 120. So what is the value of p? P is equal to 6 and n is equal to 1000. So substitute this value, you will get the value of frequency. And the same frequency can be substituted here, f, and what is phi? Phi value is 0.5 Weber and t. So remember, here the task is to find the value of t. Of course the Kc and Kd values are given. So here what is T? As you know, T is equal to Zph divided by 2. Zph divided by 2. And what is Zph? So you have to be very careful while simplifying Zph. Look at the problem here. Even though the poles are given in the problem, but here it is given as, because you know that Zph is equal to, the equation is number of poles into, so number of slots per pole, correct, into, so number of conductors per slot, right? So what is Zph finally? Of course this divided by 3. Now what is Zph finally? So Zph is nothing but the number of conductors. So finally we should get the number of conductors. And look at the values given here. Even though the poles are provided here, you need not to substitute the poles, because directly they have given 90 slots. They have not given 90 slots per pole. Okay, 90 slots per pole is not given. They have directly provided the value of 90. So you can ignore this part. You can ignore number of poles here. So they have directly, since they have directly given the number of slots here, you can substitute 90. Okay, so you can substitute 90 into, so 12 conductors per slot, 12 conductors per slot, because when the number of slots and slot gets cancelled, so you get number of conductors. So we need to substitute the value of only number of slots here, because since they have not provided this value as slots per pole, Remember, if this is provided as number of slots per pole, then we need to have the number of poles also in the same problem. But since it is given as only number of slots, you can directly have this, you can ignore this part, you can ignore the number of poles here. And finally it is 90 into 12, so divided by 3. Okay, so simplify this Zph and substitute here to find the value of T. Finally substitute the value of T over here and substitute Kc and Kd, so you will be getting EPH value, and later substitute this EPH in this equation to find the value of line EMF. Now look at the values here. We have got Zph as 360, then T as 180, because Zph divided by 2, and the frequency which we have obtained from this is 50 Hertz. Substitute all the values over here, then you will be getting EPH as 19380.6 in terms of volts. Okay, and substitute this value here, that is in EL is equal to √3 EPH, then you get the value as 33568.0 volts. Okay, in this way we can calculate the value of EPH and E line. Thank you.